Greetings, everyone. Welcome to my YouTube channel for Kangaroo Maths and Science Academy. Tonight, I want to take you through the electrostatics, which is for part 2, where in part 1, we went through Coulomb's law. We stated Coulomb's law. We also went through on how to calculate the net electrostatic force at a point charge due to other point charges. Now, ladies and gentlemen, I want to take you through the electric fields and electric fields at a point. This is for both grade 11 and 12. All right, I believe you will enjoy the session. Kindly like, subscribe, and share the video. And also, don't forget to hit the bell button for future video notification. All right, without wasting time, ladies and gentlemen, let me share the screen for what I want to address tonight. All right, since this is our part 2 for electrostatics, first of all, I will first address some of the concepts which we should have done in first part. But now, however, in the meantime, if you have not went through the first part for electrostatics, kindly do so that it will be easier for you to understand the second one. All right, tonight I want to take you, as I said, I want to take you through the electric fields and electric field patterns. I'm going to say electric field at a point. All right, now, without wasting any time, first of all, you realize that in the first part, as I said, we went through electrostatics for grade 11, where we went through Newton's laws of, I'm going to say Coulomb's laws, where we stated the Coulomb's law in weights, where we also looked on how to solve problems using the equation F equals to K, charge 1, charge 2 over R squared for charges that are in one dimension. And also we went through the problems where we looked on how to determine the electric field at the point when we are having charges that are in 2D, particularly when they are in a right angle triangle, where we use a tail-to-head method in determining the resultant or the net electrostatic force at a point due to other point charges. Now, without wasting time, I want to take you through electric field, ladies and gentlemen. First of all, one must be able to know what we mean by an electric field and also what we mean by an electric field at a point. All right, electric field is a region of space in which an electric charge experiences a force. A region of space in which an electric charges experience a force is called an electric field. So you must differentiate between electric field and electric field at a point. Particularly, we'll be talking about how to calculate the electric field or the electric field strength at a point due to other point charges. Right, and these are electric field as a region of space in which an electric charge experiences a force. The direction of the electric field at a point is the direction that a positive test charge would move if it is placed at that point. So this is what we'll be talking about when we actually calculate the electric field at a point. Then again, you must be able to draw electric field patterns, particularly when we have a single point charge. Let's say we have a positive charge. And how do we draw the electric field pattern? We know the electric field lines must not touch each other. So you will have something like this. But on a positive charge, we know the field lines, they go outwards in terms of the electron transfer. So it means this is the direction of the electric field lines. They have to go outwards. Wherever, when we have a negative charge, then they have to go inwards. So it's very, very important to be able to understand that on a positive charge, electrons are actually removed. Electrons are actually removed. But on a negative charge, the electrons are actually added. So this is what we'll be talking about when we actually dealing with the electric field patterns. So why I'm saying this is that if we have 2-point charges where we have a positive charge and a negative charge, what will happen? We're going to have an attraction. We know where we went through that like charges always attract each other. So what does this mean in terms of the electric field pattern? It means you're going to have something like this. So we're going to have something like this. So this is what we'll be having in terms of the electric field patterns. I apologize. So we'll have something like this. So in other words, it means that since the 2-point charges are unlike charges, so it means we'll have an attraction, and this attraction will mean that a positive charge will have to have an outwards in terms of electron transfer. So it means the direction of the electric field lines always moves from positive to negative. So it means in the negative part, they go inwards. So what does this mean? It means the electrons are removed on the positive charge and they're actually added on the negative charge. So you need to be able to understand the difference between charges that are removed and also the one that are added. So this is what you need to be able to understand. And again, you need to be able to define an electric field at a point. And it's very important, guys, in the examination to be, sometimes they say, define the term electric field. And if you define the electric field as electric field at a point, then it's wrong actually. So electric field at a point is the electrostatic force per unit positive charge placed at that point. So the electrostatic force per unit positive charge placed at that point. So this is the formula for calculating the electric field at a point. So it means E equals to F divided by Q. So this is actually called, the E stand for electric field at a point. So in other book, they call it electric field strength. And this electric field is measured in field at a point is measured in Newton per Coulomb. Why? Because the F, it is our electrostatic force, which is actually measured in Newton. Then the Q is the charge, which is actually measured in Coulomb. That's why we said the electric field at a point is the electrostatic force per unit positive charge placed at that point. And now, this Q here is actually called a test charge, which means when we are calculating the electric field at a point, we can either use this formula or we use the KQ over R squared. And why are we using KQ over R squared? Is that it means this is the source charge. It is the charge that is actually producing the electric field lines. So what do you call this a source charge? Is that, okay, I apologize, let me use small letter Q here. I apologize, guys. So it's force divided by Q. So it means this Q is actually the test charge. We usually call it a test charge. So now, why am I saying when we are calculating electric field at a point, we can use force multiplied by the test charge, or we can use a K times Q over R squared? Is because of I think I'll explain this while we are going to deal with the examples. So it means this is the formula for calculating the electric field at a point. As I said, it is the electrostatic force experienced per unit positive charge placed at that point. So it's very important for you to be able to know how to actually calculate the electric field at a point, ladies and gentlemen. Right, let us now go through the example. But before I go through the example, guys, in the previous video, we went through how to calculate the net electric field at a point, but I indicated something that we need to be able to deal with charges where they actually acting maybe together with the tension and other type of forces. So now this is what I want to address before we move on to electric field at a point and how to draw the electric field patterns. All right, let's now deep dive into the questions. Right. If you do not understand what I just said or something like along the way, kindly make comments in the in my YouTube channel. Then I will be able to attend to you as soon as possible. All right. Without wasting time, ladies and gentlemen, let's now continue. Right. I'll just go through one example, which is actually related to part 1, but it's also applicable to what we're going to address now. Here it's an example. Like it says, a very small graphite coated sphere, a very small graphite coated sphere, P, a very small graphite sphere P is rubbed with a cloth. So it means they're rubbing a sphere P with a cloth, and it is found that this sphere, the sphere has acquired a charge of 0.5, has acquired a charge of 0.5 microcoulomb. Then the question says, calculate the number of electrons removed. Calculate the number of electrons that are removed from sphere P during the charging process. Calculate the number of electrons that are removed from the sphere P during the charging process. Why are they saying that are removed? It is an indication that sphere P is actually a positive charge. It's actually a positive charge, which is the one that releases electrons. So it means electrons becomes removed on it. So now it means we want to know the number of electrons that are removed from that sphere P when it has acquired a charge of 0.5 microcoulomb. But this specifically for grade 12, where we calculate the number of electrons. Right, there is a formula that we use to calculate the number of electrons in electrons, which states that number of electrons is equals to the charge of that particle divided by the elementary charge on the small letter q. So in other books, they use small letter q. So it means we now are going to take the source charge, we divide by the elementary charge, and the elementary charge is given in the formula sheet. Right, if you look down there in the formula sheet, we have the elementary charge, charge of an electron. Yes, electron charge, which we can call it as elementary charge. It's always equals to minus 1.6 times 10 to the power minus 19. So this is the value here. It is the value that we are going to use. But now, if our charge is negative, then we're going to use negative 1.6 times 10 to the power minus 19. But if the charge is positive, then we are not going to use the minus sign. So it's 1.6 times 10 to the power negative 16 coulomb. So this is our charge of an electron or elementary charge. So now we are going to go back to our question so that we are able to answer the question. Right. Without wasting time, as I said, now we want to know the number of electrons that are removed from the sphere P during the charging process. So how are we going to do that? We are going to look at the charge of that the amount of charges that sphere P has acquired. It has acquired a charge of 0.5 times 10 to the power minus 6. So this is the charge acquired. Divide by the elementary. Remember I said elementary is minus 1.6 times 10 to the power minus 19 coulomb charge of an electron. So now, since our charge here is positive, so we're not going to use the minus. It will be 1.6 times 10 to the power minus 19. Then we are able to get the number of electrons that are removed from sphere P in the charge during the charging process. 0.5 exponential negative 6. Then we divide by 1.6 exponential negative 19. So this will give us 3.13 times 10 to the exponent 12 electrons. So this is the number of electrons that are actually removed from the sphere P during the charging process. So it's very important for you to be able to know how to calculate the number of electrons. The formula is actually provided in the formula sheet. So you need to be able to understand this. And sometimes, guys, they can give you the number of electrons and they want you to know they want you to calculate the charge of that sphere, or like it depends with the equation. Right, without wasting time, let's now move on. I want us to move on. We have now calculated the number of electrons that are removed from sphere P. Reason I said, guys, when the charges are removed, it means they're removed from a positive charge. When electrons are removed, it means that charge is actually a positive charge. Why? Because electrons move from positive to negative. So it means on a positive charge, the electrons are removed, and on a negative charge, the electrons are actually added. So it's very important to know that. Right, without wasting time, let's now go through the next statement. The next statement, it reads thus: now the sphere charge, now the charge sphere P is suspended from a light inextensible string. So you see, we are dealing with electrostatics that has to do with Newton's laws here, because we have to use the forces here. So they told us that the sphere P is suspended from a light inextensible string. So it means we have a tension here, because the force on a string is called the tension. Now, another sphere P with a charge of negative 0.9 microcoulomb on an insulated stand is brought close to sphere P. And as a result, sphere P moves to a position where it is 20 centimeters from R. So it means now this is the distance between sphere P, which is a positive charge here, and sphere R, which is a negative charge here. So now, and they're saying they're at a distance of 20 centimeters apart. So we need to convert that distance. Now, as shown in the diagram, but they said the system is in equilibrium. The system is in equilibrium. It means this is now taking us through the issue of equilibrium system in terms of resultant of forces. Now we know that when they say the system is in equilibrium, they are referring to the issue that all the forces that are acting here are balanced. And if the forces are balanced, it means the net force that is acting on the system is zero. So the net force acting on this system is zero. So it means we are dealing with balanced forces. Balanced forces. So the forces are actually balanced. And since they're balanced, it means the net force that is acting on the system is zero. Then the angle between the string and the vertical is 7 degrees. You see that this string now is acting at an angle of 7 degrees. And we know when we are dealing with vectors, any vector that is acting at an angle should always have components. We need to resolve that into components. So since we have our tension here, we are going to construct the right angle triangle so that we can have the components of that tension, because the tension is acting at an angle of 7 degrees. And how do you do that? We're going to use tail to head method. So it's going to be tail to head. And from here, we have the tail to head. So tail to head with an angle of 90 degrees. So we're going to have this. So it's going to be tail, we're going to have tail to head. And from here, we put another tail to head. And how do you see that we've done it correctly? When there is a resultant, you must have two heads and two tails. So it's very important to know that. All right, without wasting time, let's now go through this. Why am I doing components? Is because the tension is now acting at an angle, which means we must have the components of the tension. So since this one here, it is the horizontal, I will call this the Tx, and this one is the vertical, I will call it the Ty. So already we have the components. We have the components of tension. And how do we write components of tension? We have Tx and we have Ty. But since both are the components of a tension, it means the T must be part of the equation. One must use sine and one must use cos. So it means this one, because it's the opposite, it means it's the one that will use sine 7 degrees and sine 7 degrees, and the other one will be 2t cos 7 degrees. It will be the cos because this will be the adjacent. So that will be the adjacent. But still, if we do not want to use this angle of 7 degrees, we can say CH7, it means what will be this angle here? It will be 83 degrees. We can also use 83 degrees instead of 7. Why? Because sum of angles in the triangle must add up to 180 degrees. So it's either we use 83, let me say 7 degrees, or 83 is still fine. So already we have resolved the tension into components. Now, the first question says, draw a labeled free body diagram showing all the forces that are acting on sphere P. By the way, guys, remember, an electrostatic force, it's a force like other forces. The electrostatic force, it's a force like other forces, the Fe. So what you're going to do, you're going to sacrifice. Already we have the tension. The tension is one force that we're going to represent here. And another force would be this. Remember, between charge P and charge R, these two charges are unlike charges, which means they will have an attractive force between them. And since they have an attractive force, it means the electrostatic force between the 2 point charges will also be represented when we draw a free body diagram. So it means here, when we are going to draw our free body diagram, firstly we'll have I apologize, not drawn right. So it means you're going to have the tension. The tension will be part of. Okay, so we're gonna have the tension. This is the tension. Then what will be the other force? By the way, this sphere P already has a mass. And since it has a mass and it's actually hanging, it means you're going to have force of gravity. The force of gravity will also be part of that. So we're going to have the force of gravity, the Fg will also be part of. So we're going to have force of gravity, then we'll have the Fg. And another thing is the issue of, remember, these 2 point charges, they are unlike charges. One is positive and one, it means they will have an attractive force. So they will have an attractive force, same but in opposite direction. So you see that within within sphere P, we'll have an electrostatic force. So we'll have Fe. The Fe will also be part of the free body diagram. So it means this is our free body diagram that is acting on sphere P. 3 marks 3 forces. So we have an electrostatic force, we have the force of gravity, and we have the tension. We also have the tension. So it's very important for you to be able to understand that. And another thing, guys, it's the second one says, State Coulomb's law in words. I believe you can be able to state that the magnitude of the electrostatic force between 2-point charges is directly proportional to the product of the magnitude of their charges and inversely proportional to the square of the distance between them. So that is according to Coulomb's law. Then now moving on, 5.4, it says, calculate the magnitude. You do not want the direction here. Calculate the magnitude of the tension in the strain. We want to know the magnitude of the tension in the string. And how are we going to do that, guys? We are going to do this. We know that the system is in equilibrium. So what you're going to do, you're going to say, okay, fine. How many forces here are vertical? Already on sphere P, let's say on sphere P, how many forces are vertical here? On sphere P, the forces that are vertical is 2. It's only the Ty and the Fx. So it is the vertical component of the tension and also the force of gravity. But however, I will not use the vertical component to determine the value of T. Why? Because if I'm using vertical component, it means I have to use force of gravity. And force of gravity requires the mass of that sphere P and the gravitational acceleration. We know it's non-commute, but since we do not have the mass, it means we cannot calculate the tension using the vertical forces. So what we're going to do, we have to consider the horizontal forces. Let's now consider the horizontal forces. How many forces are actually horizontal? Horizontal, we are referring to those that are directed to the right or directed to the left. Obviously, there's 2 of them. It is the electrostatic force and it's also the X component of the tension, but they are not directed in the same direction. They are not moving in the same direction. So it means we can choose right as positive. We can choose right as positive. It means the electrostatic force at P will be positive, and choose left as negative. But since they said the system is in equilibrium, we know that according to Newton's second law of motion, the net force is equal to mass multiplied by acceleration. But since they said the system is in equilibrium, it means the net force here is 0. And since the net force is 0, it means you're just going to add the 2 forces. So we're going to have Fe, which is a positive, minus the tension, Tx, and we equate this to 0. So we want to calculate for the tension, the magnitude of the tension of the string, the tension in the string. And how do we do that, ladies and gentlemen? We're going to say, okay, fine. The electric field at a point, it's now, we know Fe. Let's transpose the Tx to the right-hand side. This is equals to Tx. And guys, what do we want? We want to calculate the tension. So it means when we're calculating the tension, you must first get the electric field. I'm saying the electrostatic force between P and Q. So it means to do that, we're going to use the formula. It's K, Q1, Q2. So this will be the charge on P and the charge on R divided by the square of the distance between P and R. So which is equals to Tx. What is our Tx? Our Tx is T sine 7 degrees. So now let's now calculate. To do the calculation, the K, it's 9 times 10 to the power of 9. What is the charge P? The charge P is 0.5 multiplied by 10 to the power minus 6. And the charge R is given as 0.9. So you're not going to use the sign. 0.9 times 10 to the power minus 6. And what is the distance between P and R? Is 20 centimeter, which will divide by 100 to convert it into meter. So this will be 0.2 squared. Then this is equals to T sine theta. So we want to calculate the tension. And to calculate the tension, it means that we have to say, let's now work out the electrostatic force between P and Q. Let's now work out the electrostatic force between P and Q. Then now, without wasting time, let's now calculate the static force between P and Q. So 9 exponential 9 multiplied by 0.5 exponential minus 6 multiplied by 0.9 exponential minus 6 divide by 0.2 squared. Then this will give us the value of 0. If I'm not mistaken, it's 0.10125 equals to t sine 7. We want to make t the subject of the formula. So we divide there by 7, sine 7 degrees, and we divide there by sine 7 degrees. And this will divide, then we're going to remain with the tension. So divide by sine of 7 degrees, and this will give us a tension of 0.83 Newton, 0.83 Newton. So you see that we have used Newton's laws of motion, particularly Newton's second law of motion, and also an electrostatic force is the same. It's the same, like it's a force like other forces in Newton's laws of motion. So you need to make sure that you understand this. And without wasting time, guys, we can also determine the mass of the sphere. If you wanted to know the mass of sphere, I mean, it's another question that we can add here, because we're not given the mass of the sphere. But to calculate the mass of the sphere, I think I can edit as 5.5. To do that, to calculate the mass of the sphere, now it means you're going to consider the vertical forces, and they will also be balanced. We'll consider vertical forces. And how many vertical forces are there? As I said, there are two. We'll have the Ty, and the force of gravity. So it will be the Ty and the force of gravity. So they are not moving in the same direction. So we're going to say, according to Newton's second law of motion, since they said its net force equals to ma, but since they said the system is in equilibrium, it means the net force is 0. So, but here, how many forces are vertical is 2. It's Fg and Ty. So we're going to take Ty is positive, Fg, force of gravity will be negative. So this will be Ty minus force of gravity equals to 0. So this will give us Ty, it's T cos 7 degrees equals to Fg. And now we know the tension, so I'm just going to say 0.83 cos of 7 equals to force of gravity, it's multiplied by gravitational acceleration. So this will be 0.83 cos 7 degree equals to, we do not know the mass, but we know gravitational acceleration is 9.8. So we can divide there by 9.8 and divide there by 9.8, that will give us the mass of that sphere, P. So we're going to have 0.83 cos 7 divided by 9.8, which means this will have a mass of 0.084 kg or 0.08 kilogram. I mean, if we wanted to know the mass of sphere P, I believe, guys, you are following. I believe you are following. Right. Let us now continue. Okay. Okay, now we're going to move on to the next part. Okay, right. Oh, sorry, I think I closed the video. Okay, then now let's move on. So it means we went through part 1, topic that I wanted to address. Remember, practice makes perfect. Now let us move on to the issue of electric fields and electric fields at a point. We went through the issue of electric field, where we said electric field is the region of space in which an electrostatic force will experience. I'm saying an electric charge will experience a force, whereas electric field is the electrostatic force per unit positive charge placed at that point. So it means this positive charge that we are placing at the point, we actually call it a test charge. And guys, how do we calculate this? Is that, let's say we have a point charge, let's say we have a charge here, and we know the magnitude of this charge. We know this, the magnitude of the charge. So it means since we know this magnitude of the charge, let's say we have a point here, let's call it point X. And at this point X here, we do not have the charge. So what are you going to do? We know, okay, fine. Since they're at the distance of R between them, what are you going to do? We have to put a test charge here. Let's call it small letter q. And this test charge is the one that will be used to actually to give us the direction whether this source here, this charge as our source, will it, in terms of its electric field, will it has an attraction or a repulsion? Depends in terms of the direction. So when we are calculating the electric field at a point, what do we do according to this formula? We have to take a force at that point and we divide by the test charge, which is the small letter q. But now look at this. Since this is just a test charge, which is just used to determine the direction. If we want to change this, we can say, okay, we know that the electric field at a point is the force divided by the test charge. But now, how do we calculate the electrostatic force between 2 point charges? So we're going to use the formula F equals to K charge 1, charge 2 over R squared. So since we have two charges, we have the source and also have the test charge. So this will be K times the source times the test charge over the square of the distance between them. Then we divide by the test charge over 1. Now we're going to change division to multiplication. So we're going to have this times 1 over q. So it means the q will actually divide. You see that we have divided the what? The test charge. So it means if you want to calculate the electric field at a point, we have to consider the k times the source charge divided by the square of the distance. That's why when we are calculating the electric field at a point, since at the point we do not have a charge, we actually calculate the charge due to the source from that point charge. So this is the formula that we'll be using to actually calculate the electric field at a point. So now, while I was busy explaining this, guys, you need to also familiarize yourself with the issue of knowing that electric field at a point, or what is called electric field strength. Electric field at a point or electric field strength, it's also a vector. It is a vector. And what does it mean? It means it has both magnitude and direction. Why is it a vector? It's because a force is a vector, which means the direction of the force will always imply the direction of the electric field at a point. So it means you're going to consider the direction of the force in order to understand the direction of the electric field at a point. So it's very important to actually know that when you are dealing with the electric fields and electric field at a point. Right, without wasting time, let's now go through the examples. I want us to go through the examples. Right, now without wasting time, let us now look at the question, the statement. It says two small identical spheres, A and B, two small identical spheres, A and B, each carrying a charge of 5 microcoulomb. Each is carrying a charge of microcoulomb. So we're given 2 point small identical sphere, which has a charge of 5 microcoulomb, which is 5 times 10 to the power minus 6. So we have charge A. What is charge A? Charge A is 5 times 10 to the power minus 6 coulomb. And we also have charge B. Charge B is also 5 times 10 to the power minus 6 coulomb. And these charges are placed at the distance of 2 meters apart. At the distance of 2 meters apart. So it means now From A to P, we're told that it is at a distance of 1.25. So it means from P to B, that will be 2 minus 1.25, which will be 0.75. It means the distance between P and M is 0.75. 0.75 as the distance between P and Q. So now point P is the electric field. Point P, it is the electric field due to charge sphere and located 1.25 from sphere P. So it means from sphere A, it means this P here, there is no charge here. This is just our point. It's just a point where we're going to have an electric field due to other point. And now, remember, it's very important to remember the definitions of an electric field, because when you're going to do the calculation, so we're going to use it. So now the first one says describe the term electric field. I think that one is straightforward. I'm going to talk about it. A region of space in which an electric charge experiences a force. Then the second one says draw the resultant electric field patterns due to the 2-point charges. It means due to charge A and B. But since they're both what? They're both positive. What's going to happen? They will not attract, they will repel. So we'll have a repulsion. This is what you're going to have. So we're going to have a repulsion between these 2-point charges. So they will repel each other. So we're going to have a repulsion between these 2-point charges. And in terms of the direction, we know that the positive charge in terms of electrons are always removed. So it means this will be the direction of the electrons. So the electric field lines, they will be outwards. Even here, they will be outwards. But however, we'll have a repulsion. So this is what you need to know. Right, let's now move on. Then now the next question says, calculate the magnitude, not direction, but the magnitude of the net electric field at point P. We want to calculate the net electric field at point P. Apologize. And how are we going to do that, guys? This is what you're going to do all the time. If they ask you to determine the electric field at a point, what you have to do is you must place a test charge at that point. Why do we have to place a test charge at the point? For us to know the direction of the electric field at that point. So then now we're going to say, since we want to calculate the electric field at a point, it means we must go to the point and place a positive charge at that point. So it will be our test charge actually. So, but already we know that when we look at sphere A on its own, it's a positive charge. And sphere B on its own, it's also a positive charge. So it means what we're going to do, we have to place a positive charge on the point so that we be able to know the direction of the electric field at point P. Don't forget, the direction of the force, it is the direction of the electric field at a point. Now, one other thing is that since we want to calculate the electric field at a point, electric field is calculated by using Q over R squared. So it means, what does it mean with the distance? The higher the distance, the lower the electric field. So we can be able to know which one will have the highest electric field and which one will have the lowest electric field. So step number one in answering this, we have to draw a vector diagram. We have to draw a vector diagram or a free body diagram to represent the direction of the electric field strength at that point. So remember I said when you are calculating electric field at a point, you have to place a positive test charge at that point, as the definition is saying, that is the electrostatic force experienced per unit positive charge placed at that point. So it means at that point, if we want to calculate the electric field at point P, we need to place a positive charge at that point. So we want to calculate E net at P. And how do we do that? We place the positive charge at that point. Now we're going to take decision of whether we're going to have an attraction or a repulsion. Let's now compare the point test charge at P due to A. Since the two charges are positive, what's going to happen? the two charges will repel. So it means we'll have a repulsion in terms of the forces. So we have something like this, we'll have a repulsion. And we know that if we have a repulsion, it means the force will be the same, but in opposite direction. But now we are not talking about force, we are talking about electric field. And remember I said the direction of the force is the direction of the electric field. If this one is directed to the right, it means even the electric field will be directed to the right. So now, what can we say? We're going to say, okay, at point P, the electrostatic force at P due to A, not the force. This one, we're not calculating the net electrostatic force. You're calculating, we want to determine the net electric field at a point. So it means this will be the direction. This will be the electric field at P due to A, which will be directed to the right. Now, let us now compare the electric field at P, point P, charge P and charge B. Obviously, charge P and B are also having positive charges. So it means they will still repel when I have a repulsion between them. And when we have a repulsion between them, it means this is the force on P due to B, which will be directed to the left. So it means now, in that case, since we know that the direction of the force is the direction of the electric field at a point. So it means now the electric field at P, the electric field at P due to B will be directed to the left. But now, why did I draw in the electric field at P due to A as the one with the highest magnitude? Is because no, I apologize. The one that will have the highest magnitude is the electric field at P due to B. Why? Because of the distance. The smaller the distance, the higher the electric field at a point. So it means this one will have a higher magnitude, and this one, let me try to reduce this one. This one will have a smaller, the smaller in terms of magnitude. It will be small. Why? Because the distance between P and B is 0.75. Remember I said the higher the distance, the smaller the electric field strength, which means if the distance is smaller, it means the force will be higher, and even the electric field will also be higher. So now what we're going to do, first of all, we can calculate the electric field at P due to A. We're going to use this formula. Remember, this one uses the source. It means we do not have the electric field. I'm saying we do not use the test charge. So it means here, since at point P is just a test charge due to A, so we're going to calculate using charge on A. So it's going to be K Q on A over R squared, which is between P and A. So we're going to calculate the electric field at P due to A. So what is the K? It's 9 times 10 to the power of 9. What is the source charge at A? The source charge at A is 5 multiplied by 10 to the power minus 6 divided by. What is the distance between P and A? It's 1.25 squared. So let's now calculate the electric field at P due to A. So it will be 9 exponential 9 multiplied by 5 times 10 to the power minus 6 divided by 1.25, because already it is in meters squared. So this will give us 28800 Newton per Coulomb. Let's specify the direction. This is directed to the right. So we must write that this is directed to the right. And we do the same for the electric field at P due to B. We do the same. Remember, the bigger Q is for the source. So now we're going to say the electric field at P due to B, that will be K charge at B, not at P, divided by the square of the distance between P and B. So now what is the K? It's 9 times 10 to the power of 9. Charge of B is still the same. It's 5 times 10 to the power minus 6. Now, what is the distance between P and B? It's 0.75. Remember, the smaller the distance, the higher the electric field at at a point. So it's 9 times 10 to the power of 9 multiplied by 5 times 10 to the power minus 6 divided by 0.75 squared. So this will give us a value of 80,000. So it will be 80,000 Newton per Coulomb. This is directed where? To the left. So we're going to say to the left, if I'm not mistaken. It will be to the left, right? So now I believe you are following. Now what do you want? You want to calculate the net electric field at point P due to point A and B. So we're going to say the E net at P. How many vectors are we having? 2. Let's now this is our choice. Let's now consider the direction. The electric field at P is directed to, like at P due to A is directed to the right. So let's choose right as positive, then left as negative. So we want to get the E net. So to do that, you're going to end up subtracting. So it's going to be the electric field at A, which is a positive 1, minus, the electric field at P due to A minus the electric field at P due to B. What is the electric field at P due to A? Is 28800. Then we subtract the 80,000. We subtract the 80,000, and the answer will be negative. Remember, negative is for the direction, but since they said calculate the magnitude, it means there's no need for us to specify the direction. We do not have to specify the direction. So I believe you guys are following. Minus 1. Okay, I want to confirm something. Multiplied by 5 exponential minus 6 divided by 0.75 squared. So this is 80,000. So let's get the answer. 28800. So this will give us a magnitude of 51200 Newton per Coulomb. Remember, the minus is for the direction, which means that this will be directed to the left. But however, since they want the magnitude, so we're going to say the electric field, the net electric field at P will be 51,200 Newton per Coulomb, without specifying the direction, because they want the magnitude, not the direction, but they want the magnitude of the net electrostatic force at P, point P. So that is how we calculate the electric field at a point. I believe you guys are following. I believe you are following, guys. Let's now move on to the next. Oh, I apologize. The next question. Now, this is the first one. Then the second one, I think this one you guys can do it on your own, but I can actually guide you. It says 2 charges sphere R and S. 2 charges sphere R and S are both stationary. They're both stationary. Okay, sorry guys. Yes, 2 charges R and S are both stationary, which means not moving, on a smooth insulated surface inclined at an angle of 25 degrees to the horizontal. So we're dealing with inclined plane here. So sphere S is 0.01 kg. So we are told that the mass of sphere S here is 0.01 kg and is carrying a charge of negative 6 times 10 to the power minus 9 and is connected to 0.03 meter long by a light inextensible string. So it means there's a tension here. There is a tension because they're talking about a string which is connecting sphere P and point P there. Right, and we are told that the charge S, it's minus 6 times 10 to the power minus 9 Coulomb. Then attached to point P at the top of the incline. So it means just attached to this point here. by a light inextensible string. So now sphere R carrying a charge of 5 times 10 to the power minus 9. We're given charge R, it's positive 5 times 10 to the power minus 9 coulomb. So sphere S is negative charge and sphere R is a positive charge. Now, we are told that it is held such that the distance between between the spheres, the center of the sphere is R. So the distance between R and S is given there as shown below. Then now, what are we given? There we are also told that, okay, sphere R XZ. We are told that the sphere R exert an electrostatic force of magnitude 1.2 times 10 to the power minus 3 Newton on sphere S. Remember, let us now look at the nature of these spheres. Sphere R is a positive charge and sphere S is a negative charge. So it means they will have an attraction, same force but in opposite direction. So they will have an attraction here. The attraction force. So we'll have something like this. Okay, I apologize. So same force but in opposite direction. So we're gonna have something like this. So now, which means now we're gonna have, let me just reconstruct it, yes. So they will have the same force but in opposite direction. So the force on R due to S and the force on S due to R are equal. So we're given that the force between charge R and S is 1.2. So the first question says state Coulomb's law in weights. I believe you can do that. And the second question says calculate the distance R between the sphere. So I want to know the distance R between the sphere. And what are we given? We're given an electrostatic force. So we're going to say electrostatic force is equal to K charge on R multiplied by charge on S divided by the square of the distance between them. But already we are given the electrostatic force between point R and S. It's 1.2 times 10 to the power minus 3. We know the K, it's 9 times 10 to the power of 9. What is charge R? Charge R, it's 5 multiplied by 10 to the power minus 9. And what is charge S? It's 6 multiplied by 10 to the power minus 9. And what do we want? We want the distance between the two. So what we're going to do, we're going to cross multiply. This will be 1.2 times 10 to the power minus 3 R squared, because this over 1. Then we can multiply this other one. 9 times 10 to the power of 9 multiplied by 5 times 10 to the power minus 9 multiplied by 6 times 10 to the power minus 9. So this will give us a value of 2.7 times 10 to the power minus 7. Then we divide there by 1.2 times 10 to the power minus 3 and 1.2 times 10 to the power minus 3. Then this will give us R squared. So 2.7 times 10 to the power minus 7 divided by 1.2 exponential minus to the power of minus 3, then this will give us a value of the R squared of 2.25 times 10 to the power minus 4. Then you put the root sign in between. So what is the R? The R is the root of the answer. So this will have a distance of 0.015 meter. So it means the distance between R and S is 0.015, which is actually 0.02. If we were to round to 2 decimal places, this will be 0.02 meter. It is 0.02 meter. So that is the distance between R and S. Then the next question says, draw a labeled free body diagram for sphere S. Remember, the sphere S, it is in contact with the surface. So what does it mean now? It means now the sphere S has force of gravity, has the normal force. So we're going to have a normal force here. There is a normal force and there is a force of gravity, and they said the system is smooth. It means there's not friction, so we're going to have also the tension And beside that, we're going to have an electrostatic force between the two. The Fe is also part of. So in terms of a free body diagram, it means you're going to have the normal force. Sorry. So you're going to have the normal force and together with the force of gravity, and we'll have the tension, which will be at right angle. Okay, so we'll have the tension. And another one, it is the electrostatic force, Fe. So we'll have an electrostatic force between the 2 point charges. Okay, apologize. So I think this is big. It's long actually, not necessarily big. So we'll have the force of gravity, the weight there. So this will be our force of gravity. So these are the components. I'm saying it's our free body diagram. So we have the electrostatic force between R and S already we have the tension, we have force of gravity and the other. Right, then the next question says, calculate the tension in the string. We want to know the magnitude of the tension in the string. And how we're going to do that, ladies and gentlemen, we can use Newton's laws in determining the tension on the string. But now we know that since we are dealing with an inclined plane here, it means we have to resolve the force of gravity into components. We have to resolve the force of gravity into the components because we want to know the tension. And how we're going to do that, it means now we have to show all the forces that are actually acting on the system. And even like, because we have an inclined plane, it means the force of gravity need to be resolved into components. So already we have this. I'll first say the force of gravity was supposed to be here, which means if the angle is 25 degrees, it means we are going to have 25 degrees there. And because of that, we have to make components. It means we're going to have tail to head. And from here, we have tail to head. So we'll have tail to head, tail to head. So 2 heads and 2 tails. So when I use tail to head in determining the components. So, and another thing very important, guys, this tail to head, tail to head. Remember, there's an angle of 90 degrees. So it means this is the component which you call it FG perpendicular because it makes an angle of 90 degrees with the surface. And also this is the FG parallel. So it means we have components of FG. Let me just use the other color. So now this will be the FG perpendicular, force of gravity perpendicular, and this will be the FG parallel. So we have components of force of gravity on sphere S. We have FG perpendicular and FG parallel, which will both have FG. One must use sine, one must use cos. What is our angle? 25. So it means this is the opposite. It's the one that will use sine 25 degrees, and this one will use cos 25 degrees. But we know FG, it's mg. It's mass multiplied by gravitational acceleration. So it means we can rewrite that and say FG perpendicular and FG parallel. So this will be mg cos 25 and mg sine 25. Now we want to know the magnitude of the tension. Already, let's check how many, like our tension here is the horizontal force. And since the horizontal force, how many horizontal force are we having here? There are 3. It is the electrostatic force, it is the FG parallel, the horizontal component of the force of gravity. Because if it's here, if the force is here, is the same as being here. It's one and the same thing by using parallelogram method. So now it means we're going to have the horizontal forces actually 3. So in that case, since we have three horizontal forces, now we have to consider the direction. They are not moving at the same direction, to the same direction. I mean to say, one is directed upwards and the other one is directed. Actually, let me say one is directed to the right and the other one is directed to the left. So we have the tension there. This time around, there is the electrostatic force, the Fe, and also we have the, what is the other one? The Fg parallel. So they're not going the same direction. We choose tension as positive, and the rest as negative. So it means the right as positive, left as negative. But they said something. According to Newton's second law of motion, the net force is equals to mass moved by acceleration. But they said the system is stationary, which means the net force here is zero, not moving actually. So now what does this mean? It means that now we're going to say tension minus Fe minus Fg parallel equals to zero. Let's make tension the subject of the formula. So this is the electrostatic force plus Fg parallel. And what is our electrostatic force? We do have a given, it's 1.2 times 10 to the power minus 3 plus. What is our Fg parallel? Fg parallel uses mass times 9.8 sine of 25. And guys, what is the mass of sphere S? I think they gave us the mass of sphere S. The mass of sphere S is 0.01. So you can see here it's 0.01, the mass of sphere S. So let's now do the working. 0.01, it is the mass of sphere S. Okay, let me check something here. Okay, we're given 5 exponential minus 9, 6 exponential minus 9 by 9 exponential 9. Okay, all right. Then now, the mass of sphere S is 0.01. Let's go back to our calculation. So we're going to say right now, since we have all the information here, right, we're going to say the mass of sphere S is 0.01. We got that. So let us now calculate the so this will be mg mg sine 25. What is the mass? 0.01. The g is 9.8 multiplied by sine 25. Then this will give us a tension. So the tension will be 1.2 times 10 to the power minus 3 plus 0.01 times 9.8 sine of 25. This will give us the tension of 0.04. So the tension is 0.043 Newton, which is actually 0.04, if I'm not mistaken. So there are three forces that are actually horizontal. So now, then the second question says, calculate the net electric field at point P. The net electric field at point P, which means we want to calculate the net electric field at point P due to point S and due to charges S and charges R. Let us do that. Let me find a space where we can do that. So let's now start with the calculations. We got that the distance between R and S is actually 0.02, which is 0.015. So we're going to use that to calculate the electric field at point P due to charges P and R. So let's now do the calculations. Let me confirm this for the last time. Calculate the net electric field at point P. So, okay. So I want to check the distance. We got the distance between, so it's 2 okay, 9 exponential 9, 5 exponential minus 9, 6 exponential minus 9, then divide by Okay, did I'm okay, divide by 1.2 exponential minus 3, and the square root of an answer. Yes, it's 0.02. So what we're gonna do is, okay, fine. Yeah, we can also do it here. So we want to calculate the net electric field at point P due to, so it means now we have a charge R and the other one is charge S. Now we were at this point, so we want to calculate the E net at this due to charge S and P. Remember, charge R is positive, charge S is negative. So what is the distance between S and R? We just calculate, we got 0.015. So what is the distance between P and S? The distance between S and P, it is 0.03. So it's 0.03. We can actually round this to 0.02 if we were to round to the nearest. So let's round to 0.02 because we got 0.15. So what are we going to do to calculate the electric field at the point? Then we have to go to the point and place a positive test charge in order to look at to consider the direction. Now let's compare electric field. Now the point P and S. Point P and S, they have unlike charges, so it means they will attract. So we have an attraction. So this will be the force on P due to S. So it means because we want to know the electric field, it means this will be the E instead of F. So the electric field at P due to S will be directed to the left. Then how about the electric field at point P due to R? They're both positive. It means they will have a repulsion. They will have a repulsion. So this is the electric field at P due to R. So the electric field at P due to R will be directed to the right, but it's the one that will have a smallest magnitude. Why? Because the distance between P and R is 0.05. So we're adding 0.02 and 0.03, which is 0.05 or 0.045 if we do not round to two decimal places, especially for the distance. So you see that we're going to have two components: is the electric field at P due to R and electric field at P due to S. So let's calculate that. The electric field at P due to R, at R there's no charge, so this will be KQ, which is the source. Our source is R over R squared, which is the distance between P and R. So this will give us a distance of 9. I'm saying 9 times 10 to the power of 9 is the K. What is charge R? Charge R is given as 5 times 10 to the power minus 9. What is the distance between P and R? The distance between P and R from here up until here. So it's 0.02 plus 0.03, which is 0.05. So we're going to have 0.05 squared. Then let us get the electric field at the point. So it's 9 exponential 9 multiplied by 5 exponential minus 9 divided by 0.05 squared. So this will give us 18,000. So this will be 18,000 Newton per coulomb to the, what is all to the right? Newton per coulomb to the right. Now let us calculate the electric field at P due to S. So this will be KQ at S over R squared, the distance between P and S. So what is the K? K is 9 times 10 to the power of 9. QS, we know for the negative charge S, it's 6 times 10 to the power minus 9. So what is the distance between R and S? Between R and S, it's only 0.03 squared. And we can now calculate them. So it's going to be 9 exponential 9 multiplied by 6 exponential minus 9 divided by 0.03 squared. 0.03 squared. That will give us the magnitude of 60,000 Newton per Coulomb to the left. So now, how do you calculate the E net? To calculate the E net at P, now we're going to do this. We can choose, because they said calculate the net electric, they do not say magnitude and direction. So we can choose right as positive, left as negative. So this will be EP at R minus the EP at S. What is the EP at R? The EP at R will be 18,000 minus the 60,000. So this will give us a negative value. So that will be minus 42,000 Newton per Coulomb. But since the minus is for the direction, it means the electric field, the net electric field at P at N due to P, it will be 42,000 Newton per Coulomb. The minus is for the direction. We have chosen left as negative, so it's going to be to the left. It will be to the left. I believe you are following. So that is how we calculate the net electric field at a point using this. So it's very important to know how to calculate the net electric field at a point. So, right, kindly like the video and share it with your friends. I believe you are enjoying and you are well. Thank you for listening, ladies and gentlemen. Have a wonderful night. Bye-bye.